So we know now that if you have log, it means log base 10, and if you have ln, it means log base e. So that's really just the same as log base e. So why do we even care about these? Well, the reason we use log base 10 and ln so much is because we have buttons in our calculator, and actually ln models so much in natural nature. Natural nature. Anyway, like e to the x models all of these natural processes so well that we use ln and e for lots and lots of things. And log base 10 is easy because it's easy to think in multiples of 10, 10, 100, 1000, and so on. So these are our two ones that we use on a very, very regular basis. In fact, we're going to eventually, you kind of switch to only using these. In calculus, we almost never use other log bases. We basically just use ln and log base 10. So let's evaluate some stuff and let's think about what this means. So ln of e. So remember, the answer to a log is the exponent, and it says, what exponent do I need on the base to get the argument? Well, what's the base of ln? It's really the same, and you don't have to rewrite it this way. In fact, I suggest that you probably don't rewrite it this way. But think about it in your head that log base e is the same as ln, right? So what exponent do I need on the base to get the argument? So e to the what equals e? Well, that's 1, right? So ln of e is 1. This is something you should probably have memorized. If you don't have it memorized, you can figure it out pretty quickly. But ln of e is 1. It's actually really, really useful. Okay. Log of 1. Well, that says 10 to the what equals 1. Well, how do I get 1? That would be 10 to the 0 equals 1, right? So x equals 0, therefore log of 1 is 0. In fact, log base anything of 1 is 0 because, 2 to the what equals 1? 0. 5 to the what equals 1? So any base of log is going to give you 0 out. What about this one, log of 0? So that says if I take 10 and I raise it to some exponent, what exponent do I need on 10 to get out 0? And you're like freaking out because you're like, I don't know. This is one of those hard things like fractions or negatives. No, there is no number that gives us 0. There's no number that I could put into this that's going to give me a 0 out. In fact, if you think about the graph of 10 to the 0, or 10 to the x, sorry, it looks something like this, right? It has an asymptote right here at 0, and it approaches that point, but it never actually gets there, right? Because if you think about, this is at time equals 0, I have exactly what I started with. At time equals 1, I have 10 times what I started with. At time equals -1, I have 1/10 of what I started with, and then I have 1/100th and 1/1000th. But I can never actually get down to 0 because every time, so say I have this thing and it's like, this much, right? And then at time equals -1, I get this much. And then at time equals -1, I have this much. But I can keep just cutting it and cutting it and cutting it and never actually become 0. So this does not exist. There is no number on this earth that you could put in here and get out 0. What about this, log -1? So again, 10 to what equals -1? Let's think about the graph again. Is there any number on this beautiful earth of ours that we could put in and get a negative number out? Because if you look, if I put positive numbers in, I get big numbers. If I put negative numbers in, I just get really small fractions. But there is not a number in this world that if I put it in, I'm going to get out a negative number. So you cannot put a negative number into a log. It just doesn't work. So again, does not exist. You cannot have a negative argument, okay? So log of -52 doesn't exist. ln of -3 doesn't exist. Log base 127 of -0.5 doesn't exist, okay? Because you cannot get a negative number out of an exponential function. Exponential functions never, ever, 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 ever spit out negative numbers. Therefore, this argument can never be negative.